Hey, maybe physics sounds so much more logical in Egyptian, Arabic? Arabic. My apologies. I guess Egyptian is not a real language?
Yeah, no.
Okay. I guess like Mexican is not a real language?
Yeah.
Maybe Spanish.
I don't know why they was classifying them as different, because there's a big difference between Spanish. Speaking
It's just the
Spain,
verbs that are different.
Mexico, just like English, we speak English, big difference.
Yeah, but
between-
you know, American English. So
Yeah,
Yes,
exactly.
Egyptian,
See, my-
Arabic,
they should call it
okay.
American.
There we go.
You ever talk to someone from Rhode
You
Island?
should call it
I
American.
guess I just stopped my sentence too soon.
Yeah. Let's say, ever talk to someone from Rhode Island?
But anyways,
Thing?
this is kinda like, well,
It's like
not this
Tennessee.
problem,
Yes.
but it's kinda like a coil, a car, a
That's
truck.
exactly like
Going down the
in a
road,
car.
you hitting a
Car
bump,
truck.
compacts, and then it goes back past equilibrium, and then it comes back to equilibrium, and then goes below it and driving down the road.
You know what I mean?
And the only difference, and the difference between what we're doing now and that, is if you look at a real spring like that,
Yeah.
the oscillations are doing this, and we're assuming a nice ideal that
Perfect,
it would do that forever.
okay.
That means your damper's bad.
Right. Or it's a cheap vehicle, like the ones I buy.
You get in the car.
It's
you
probably
can
just
break
got
all
over-
the balancing and
Yeah.
everything. Free hydraulic.
All right, questions, I'm gonna do one more, sliding down a ramp problem, throwing one more twist into it. Any questions on this before we do a sliding down a ramp into a spring?
Oh, bring on the plot twist.
I'm guessing some friction.
I did have one question. Over the summer, I was working at a place and this guy was telling me about springs that naturally have like a force, like a torsion spring or something. Is that like do they like always apply like some force just
You're talking about
I mean-
progressive spring?
sitting or,
I mean, any spring, whether you're dealing with torsion or dealing with just compression or stretching, you can take a spring and you can, like on a pin, like a clicker pin, the spring is always compressed a little bit.
But
Is
it-
there already a force acting on it?
Yeah, I mean, it's not in its natural equilibrium position.
But you're saying something like they apply force in natural equilibrium. It's not the definition of equilibrium.
Yeah, I'm not quite sure what they're.
maybe I misunderstood what he was saying.
What was
Maybe
he didn't know what he was talking about.
That- I'm just gonna have a force. No, sir.
And a couple of years ago, I had might have been Navy Reserve, but he was a Navy guy, he'd done a lot of electrical work. And so he occasionally asked me about these components that I'd never heard of before. The physics, not engineering. My engineering was mechanical engineering, and that was 35, 40 years ago. So,
You remember everything, right?
yes, exactly.
Yeah, sometimes electronics are magic.
Why my day that didn't exist.
I just remember one of the,
from calculus.
everyone who's, everyone who's in my class now is engineering. Operation amplifiers, magic.
He never went to school.
Please score them by, because I can't.
Wow. I was like, one of the reasons I chose this, like, you could give me some help with it. That's not.
How far would the spring compress? Let's make a spring constant of 25 newtons per meter, just why not? And give it a mass of 8 kilograms, again, because why not? We will keep it frictionless again. Unless
Pickup truck, wait.
tonight we were populated with masochists and we throw friction into it.
Okay,
Otherwise, I'll just wait for Justin.
that's fun.
Okay, Mr.
I did do one where it compressed, there was no friction when it compressed, and then,
Magically there's.
yeah, friction magically appeared.
Ew.
Sprinkled it on.
All right, so it's gonna go 5 meters before it hits the top of the spring here. I'm not worried about size of box or anything like that. So this is equilibrium position for the spring. That's its natural length without any additional forces being added to it. It is massless, so we're not worrying about gravitational pull on the spring, because it is an ideal spring. Again, we have the same three forces involved here as we did in the last problem. Again, normal force doesn't do any work. I'm not considering the normal force between the spring and the box, because that really is what we're calling the spring force, which is conservative. So we start out exactly where we were before. Energy is conserved. All right. That is the exact same place as we were before. Again, we're dealing with maximum compression here. So delta X max equals what? So we have all this energy that starts out as gravitational potential. As it slides down, that gravitational potential is going to get smaller and the kinetic is going to get bigger. Then it's going to hit the spring. And so that gravitational potential will still get smaller because it's still going down the slope, getting closer to the center of the Earth. But the kinetic will start to drop also, because it's going to start to slow down as soon as it hits the spring. Actually, not necessarily. Kinetic might go up a little bit. We can also figure out the point at which it does start to slow down. And then the elastic potential will start to increase as it compresses. So in the end, all that initial gravitational potential will be in the spring.
Initial speed is
We started.
Unless you'd like it to be a different number.
Nope. Zero is fine.
Let's zeros.
All right, so 0.
Yep. Well,
There is a trick here about trying to figure out where do you want H equal to 0.
where do you want it?
Let's see.
well,
Where the spring is
Yeah.
fully compressed?
Some mysterious place.
yeah,
So,
where we don't know actually.
so why don't we call this X? Technically it's delta X, but we'll let delta X equal X.
Or 1/2 KXI squared is 0.
Initially, so it's,
Yes, that's natural.
okay, 0.
So the final height is 0. Final speed is also 0.
There is an advantage to picking the height is equal to 0 at the point where it hits the spring. It's all a matter about where you want to put the work. The intellectual work, not the definition of work. So we have mgh initial equals 1/2 kx squared. I can get away with just saying x instead of delta x because I define how much it compresses by the letter x here. All right, so initial height.
5
It's
sine 53.
What's that? In? We can do better than that. Or we can do that as a temporary measure.
well, it's not 5. It's 5 plus x.
Sine.
No, it's not, it's the, we have to get the triangles for both. And then.
We could treat it as 1. This is 5 plus x. We can. That is
yeah,
legitimate. This is the 53-degree angle. So the height here. Of 53 degrees, which is 0.8-ish. So 0.8. 5 plus x. So we have mg 5 plus x sine of theta. equals 1/2 k x squared. We are going to end up with a quadratic. So I have, it disturbs me to put in numbers this early, so why don't we let theta equal that and let that equal L. So this becomes mg sine theta plus mg sine theta.
Did you let,
5 plus x is, well,
oh,
wait, you
You
said
just
5
said-
equals L or 5
oh.
plus x equals L?
I said 5 equals L.
So it would be L plus x.
Where'd the 5 plus x go?
did you distribute?
I distributed.
Oh.
Sorry, skip this step apparently. So this is mg sine theta times L plus x equals 1/2 k x squared. X is our unknown here. So we set up the quadratic. I have 1/2 kx squared minus mg sine theta x.
Quick question, why'd the L replace the 5?
It was disturbing me to put the numbers in this early.
So you just
That's-
deleted it and just made 5 equal L?
Yes.
Okay.
Yeah, nothing fancy. And if you, on a test or quiz, if you leave the 5 in there, there's absolutely no problem with
Okay,
that.
I was just making sure that we didn't change it for some crazy reason or something else.
No, just
Okay,
my own eccentricities.
alright, that works.
For the same reason, I'm putting everything over on the right-hand side here, because I like my first term to be positive. That's just a me thing.
Okay.
Minus mgl sine theta. And now it's solve for x. It probably is easier at this point to use real numbers.
Yeah.
So this becomes 12.5x squared minus, so we have 8 times 9.8 times sine of 53 degrees.
Oh.
62.613.
Feel free to dig out more decimal places. Minus mg L sine theta, so it's basically that 62.6 times 5.
313.065.
Feel free to dig it out the extra decimal places. X equals 62.6 plus or minus the square root of 62.6 squared minus 4 times 12.5 times negative 13.1.
Less.
That's easier. There will be 2 answers, they both have meaning. So let's get both answers and then talk about what that means.
So we have 4.05 and we have negative 1.55.
Anyone else get the same numbers? We don't.
You shouldn't.
Because Nick says so.
You really shouldn't.
Alright, listen, David's about to back you up, Nick, or shake his head in disgust.
Average unload in here.
That's not what I got.
What you got?
I got 8.1, and then I got, negative 3.09.
I did 2 times 25 instead. No, yeah, I did 2 times 25. Instead of just 25.
Oh, okay.
Cause I was thinking 2A.
It is 3.
Oh, which would explain why
300.
these answers are double what you had. David, you were working on it, did you? Yeah. I got these right here, all right. So it's what's discussed, isn't it?
Yes. Told you should trust me.
We shouldn't trust you, though, should we trust that you tell us not to trust you? Sure. Meters were there before. So the big question is, what do these two different answers mean? They both have physical meaning.
Is it
We got the answer for the. I was just trying to figure out what.
Okay.
So X is either, it's 5 meters plus, it's either 5 meters plus 8 meters away, right? So
Right, so that would be
13,
down here, yeah, 13.1 meters from its starting point.
or,
You could smash it from the other side, back to 0. The
Or-
spring.
It depends on what you mean by that.
No, well, talking about the spring, it's 8.1.
Right.
Yeah, you X, or you can go on the other side of the 0, on the other side of your hand. Like, the 53-degree angle thing, down from the end.
Oh, that.
Yeah,
that
back, yeah, right? That's the negative?
No.
Okay. I didn't know, because you're on the other side.
wait, so it's either 8 point, or,
Well, we want the meaning for.
also the
both.
spring is either 8.1
The spring
meters
does
past
compress
the starting
8.1
point.
meters from when it hits it.
Right.
It doesn't compress negative 3.09 meters.
But that does, what is the physical meaning of that negative
It's
3.09?
3.
How much
3.0.
farther out the other end it goes when it's pushing the mass out?
I figured it'd be on the other
It
side.
goes 3.09 meters past.
When you say the
Yeah.
other side.
Yeah, when it goes past its equilibrium by 3.09
All right.
meters.
Yeah.
If the mass stuck to the spring, because realize what we solved here was when the speed was 0. If the mass sticks to the spring, speed is going to be 0 here when it fully compresses. And then if the mass comes back this way, it's going to stretch out. This is what I believe Russell was saying. It's going to stretch out this way, and it will stop going this way because the spring is now stretched this far
So 3.09 meters that way.
on this side. When you said the other side, you said the other side of this, it would have been right.
Yeah, that still doesn't make sense to me. That's why I was just trying to figure. Cause I
Back to the
figured,
slinky.
yeah,
Back to the
I
slinky.
mean,
Uh-oh.
Yes, we're gonna put it on the board now.
Yeah. Can't do it.
Perfect. All right, so the mass slides down, it hits this, it compresses 8 meters. Perfect, right there, 8 meters.
yeah.
Now, the spring is coiled right now, it wants to get back to equilibrium, so it's gonna push the mass this way. So it's gonna push the mass back up the ramp.
And that's the 3.09.
And then it's gonna hit equilibrium again. If the mass attaches to the spring, then it's gonna continue past that point.
3 meters.
And
Try and get back.
almost 3.1 meters this way. And then it will stop again, and then it'll oscillate back and forth between those two.
Okay, and it
So
goes
for
up from
there's 2 questions.
the box, like the end of the X bell up is 3.09?
Yes.
Okay,
So
alright, that makes sense.
if it would slide down and get attached, then when it was done oscillating, it would be a different equilibrium length than the initial.
Didn't we make it?
I mean, it would eventually have to stop sometime.
Well, no friction. It wouldn't.
Oh, if there was friction, then
Yeah.
it would be a different resting length.
Probably. That would be a really horrible thing for me to do.
I gave him ideas, thanks.
I did do a problem, I did the mass comes down, oscillates back and forth, this separates, this comes back. And if this one doesn't go all the way back up to the top, it's gonna slide back down. And the question I asked, and it was solvable. It just wasn't as simple as I initially thought. When this mass comes back down and hits the mass attached to the spring, where is it? That was a really complex problem. And I had one student who almost got it right. It was, that was,
In your physics problem, it had like, you had the 1 kilogram mass and 100 kilogram mass. And the 100 kilogram mass is sliding towards the 1 kilogram mass. And when they hit, of course it'll bounce off and then like hit a wall. And it's like, how many times will it hit before the 100 kilogram mass?
so you want that as a test problem in the last test?
What?
No.
Stop talking.
Yeah,
They said stop.
so in a
Whatever
problem,
you wanna
like a
get.
test problem,
Because
you
I would
will
think-
ask, let's say, how far like the spring, or like how far it compresses, or how far out it compresses, it stretches. how far-
Extends. Yeah, I mean,
After
I,
equilibrium point, you might ask like either or, and then we have to,
yeah,
okay.
I usually do them as far as compresses, but.
Okay.
All right, I want to add one more twist to this, and then we'll move on to a newish topic. Any other questions on this before I throw friction into it?
New topic.
All right. It's, you know, if you can handle this, you can handle friction. You get set. All right, so let's throw friction into it. I can do it on part of the ramp or the entire ramp. Probably a little bit simpler if we do the entire ramp, actually. But, you know, you can be the judge. Work it out both ways. Let's make this 0.3. This is kinetic. We assume that whatever the static is, it's going to move. And that is for basically the duration. How far down will it compress? Now we have to be careful, we're gonna get two answers again, but one of the answers actually does not have physical sense. Because every time it moves, it's losing energy. This is no longer the case. We now have work non-conservative is equal to energy final minus energy initial. So work non-conservative plus, we just add that to both sides. So we just tack on this work non-conservative plus.
Excuse me.
said what?
So while it is sliding down the ramp, we do have friction acting on it. And force diagram, which we all know and love. This is kinetic friction, we have weight down this way, we have normal force that way, dot, dot, dot. The friction force is equal to mg, sorry, lost the mu, equals mu k mg cosine theta. Box on ramp problems, that's the friction. Is the force will be constant from friction?
Yes.
And so the work non-conservative is just going to be force times displacement. Except the friction is acting up the ramp, the displacement's down the ramp. So this will be negative friction times how far the thing actually slides. 5 plus x. Flashing back to the definition of work. Work is equal to the integral, by definition, f dot dx. If force is constant, then work is equal to f dot dx or f dot delta x. So if the force is constant, we can just do force times displacement. We don't have to worry about any calculus there. So the force is the friction force right here. And the distance it's going to be scraping along is 5 plus x. Other variations of friction starts, there's friction before it touches the spring, or there's friction once it touches the spring, or friction magically appears when it's halfway down.
Halfway down the spring, it disappears. There it goes back up.
It depends on how cool I'm thinking at the time. hopefully my better angels will go, that was a stupid problem, why'd you do that?
Just be in your happy place when you write the test.
And not sick with a fever like that poor class have suffered years ago.
Huh?
I was sick, my wife was out of town, so I had to write a final exam. That was really bad.
What'd you do, make her write your exam?
What's that?
Were you gonna make her?
No, but at least I had to step and fetch for myself, she couldn't, you know, if she had been there, she could have,
Eased his suffering, so to
Yes.
speak.
Oh,
Don't do that, Providence, very cool.
that pretty much describes the beginning, basically the many first years of our relationship. Whenever I was sick, she was out of town, whenever she was sick, I was there to wait on her. It's quite fair there.
Great
Nothing
practice.
sad for my boys.
She probably feels it balanced out.
Well, you could just take-
Because
you
I
could
was
just
gone
take-
for most of my
you could
daughter's
just take
childhood.
longer at work.
I could take longer at work?
Yeah.
Getting them sick?
No, stayed longer at work when she was sick.
Oh.
Like, take your time, grade papers here, you know. Take it home.
Next time. You know, I got plenty of opportunities in the next 30 years.
Yeah.
Alright, so we got mu k m g cosine theta times 5 minus x, or 5 plus x. All this still holds, all we're doing is just tacking on this extra bit here of this 5 as well. And so we have negative mu k mg cosine theta L plus negative mu k mg cosine theta x. And so, do the carets here. So when we bring stuff over to the right-hand side, our x term, so we got a plus mu k mg cosine theta here, and we get a plus mu k mg cosine theta L. So it's, yes, it's a lot of letters, it's an alphabet soup at times, but it's not significantly more complicated than what we've just done. All we have to do is remember that we have this extra term there. And so we, what is that, by the way?
Oh.
Is this inside the parentheses?
Yes, it's inside the parentheses.
Okay.
Which
Should
sure,
be.
wait, that's plus, that's minus, oh, that should be inside the parentheses and minus there.
Okay.
So it's,
Because this second, that's negative, we're putting that over.
It would be positive, and then
Positive.
factor the negative
Alright.
out.
So what is this?
14.25.
It's weird. See.
Where does that go? What's that?
And then this last bit over here,
The new term, where does it go?
so that times 5.
After sin theta.
Mhm.
70,
71.8.
71 point,
70.8.
70.8.
So sin theta minus.
That looks like another quadratic thing.
But indeed it is. Alright, so 50, 48.45.
Looks right to me.
And this combines into negative, let's see, so it's 0.3, carry the 1, 2, and then 2, 4, 2, 4, negative 242, 0.3.
Looks good from here.
We will get a positive and negative number answer, just like we did before.
2.87. I did 25 instead of 2 times 25. And I did negative 6.75.
Any confirmation? You just trust them, Dave?
My equation's right, that's my calculator here. Yeah, I'm not gonna follow 10 dots anymore.
People who do not trust them, anyone got it?
Should be on.
1 second.
I got 6.74. Positive.
You got positive six.
I got positive
Yeah.
6. Yeah,
I'll put it negative.
So, yeah, positive 6.74.
and then
I'll
negative.
put it negative 48. Like at the beginning, it's negative.
But it's already a negative. There's a negative right there still.
All
All right,
I'll get one right one.
Matt, you getting this? Or Matthew?
Yeah.
Okay.
Okay, so
All
it's
right,
gonna-
so,
So it's, the positive value is always gonna be is always gonna be bigger, right?
yes, I would expect that, unless something bizarre and booster rocket suddenly appeared. So which of these answers is obviously not gonna be a correct answer?
Negative.
2.87.
So that is the correct answer, that is not correct. Recognize that once it compresses and it's lost the energy from friction, this answer right here assumes it's not losing any more energy from friction. And so when it moves back up, it's gonna be losing even more, and so it will not be this high. So if we actually work out how far back up will it go if it attaches,
It'd be less, a lot less than that.
it'll be less than that.
So it'll be 6.75 below meters.
Yeah, so-
Below the natural state.
Yeah.
Yeah, okay.
Friction.
And also, we have some confidence that we've done something right here in the fact that with the friction, it does not compress as far as it did without friction.
Now, being that if this was a test, I probably forget all that. Using common sense, you're going down, so you could just simply choose a 6.75 just due to the fact it's positive value, right?
Yeah,
Okay, I just want to check.
just be careful of the wording of the problem.
Okay.
Make sure you.
And, as always, show your work
Alright.
Double check, plug it back in, see it work.
in a very clear font. Any questions?
It's my own font.
So,
Heard so.
what is the total energy compared to the first time that's left?